In this video, we're going to introduce asymptotics, or asymptotic descriptions of the growth of functions, to use a longer phrase. So, what are asymptotics? We are going to consider asymptotic analysis. So, an asymptotic analysis is a qualitative and approximate description of the behavior of a function that I'll call f with an argument n as n grows large. And in these videos and in most of our, actually all of our examples, we are going to be assuming that n is in the natural numbers. So we could be looking at functions with arguments that are real numbers or integers. We're mostly not going to do that. We're going to focus on the natural numbers n. So the reason that we would want to give a qualitative or approximate description of the behavior of a function is that there are functions that we care about that are really not possible to describe precisely and mathematically. So here's two examples. So one example of a function we care about, f of n, is the number of steps required for merge sort. So remember the merge sort algorithm from our last set of videos. F of n is the number of steps required to execute that algorithm with a list of size n. Now, in the last set of videos, we did learn that under a specific assumption about n, if n is a perfect power of 2, then we can actually figure this out exactly, at least in the worst case. But n is not always a perfect power of 2. Maybe you want to sort a list of size 127 instead of 128. In that case, actually figuring out what's the mathematical description of f of n exactly is very difficult and not really that rewarding. And so instead of trying to exactly describe f, we instead want to give a qualitative and approximate description of how f behaves. Another example that we often care about, and this comes up a lot in numerical algorithms and machine learning, we might say that f of n is the error remaining if we're trying to approximate something or find the best version of something. It's how close we are after running an approximation algorithm for a total of n steps. And so we might want to be able to say, hey, if we run this algorithm long enough, we'll get an error that's relatively small, and we can give a qualitative or approximate description of that error as the number of steps grows large. So here's the picture that we're going to think about, and we're going to focus on this picture, then we're going to look at an intuitive idea, and then we're going to state the formal definition. So here's my picture, and what I'm going to do is I'm going to imagine, okay, I have an axis with my argument n, and n is growing large, and I have a function that I'll call f here. So my function f is going to look complicated and maybe kind of wiggly, not really the kind of thing that I'm able to kind of have specific exact mathematical control over. So this is my function f of n, and maybe let's just rein it in a little bit there. All right, so there's my function f of n. And what I'm going to do is I'm going to compare f of n to a different function that I'll call g of n. So here's my function g of n. And here, for reference, is also my function minus g of n. So that's just the reflection of g of n across the horizontal axis. And what we'll notice here is that f of n is not really bounded by g of n. F of n kind of goes outside the green cone here. And so I couldn't say that f of n is smaller than g of n in any meaningful way. But what I'm going to also plot here is another pair of functions. And what these functions are c times g of n, where I've picked some constant c, and then minus c times g of n. So I have a bigger cone. My cone is allowed to become wider, if you will. And what I notice about this choice is that, at least in the way I've drawn things here, past about this point or so that I'll call n naught, it's the case that f of n is contained within the bigger green cone, the one that's scaled by c here. So it's not the case that f of n is always less than g of n, but it is the case that if I multiply g by a constant and only assume that n is a pretty large number, bigger than whatever n naught is, then it is true that f of n will be contained in that larger green cone. So this motivates my mathematical idea here. So here's my idea. If a function f of n stays within the bounds c times minus g of n and c times g of n for some constant c that can be any real number forever, if this is true forever and ever and ever, so I need this picture to kind of continue off into infinity. If this is true forever and ever and ever, once n grows large enough, so in other words, we're only thinking about n past this point here, whatever it might be, so past here in this region is our definition of large enough. If that's true, then we say that f of n is in the set of big O of g of n, or simply f of n is big O of g of n. So big O is a new symbol here. Big O of g of n says that f of n qualitatively grows no faster than g of n for large n. So this is our idea here. When we say f of n is big O of g of n, we're thinking about a picture like this, where if I have this cone with my bounds g of n multiplied by a constant, then if n is big enough, f of n is going to stay inside that cone. So now that we have an intuitive picture of what big O means, let's move on to some examples. So let's go ahead and do some examples. So in all of these examples, I'm going to consider the same bounding function that I'll draw linearly this way. And this function is just going to be g of n equals n. So I'm going to be asking myself, in other words, is it the case that f of n is in big O of n? That's what I'm going to be asking myself here. So the first function that I am going to study is the logarithmic function. So here it is. I'm going to do my best to draw it. So here's a standard kind of plot of the logarithmic functions. This is f1, I'll call it, of n is log base 2 of n. The base here doesn't actually matter. The same result would be true for any choice of the base. So you can kind of imagine if we continue this picture off to forever, and if you remember what the plot of the logarithm looks like, indeed, this logarithmic function is going to always stay within this green cone as we extend n off farther and farther. And so we would say, indeed, that f of f1 of n is in big O of g of n, or just a little more casually, we would say that log 2 of n is in big O of n. So both of those mean the same thing. Okay, so that was one example. Let's do another one. Here is the function that I'm going to try to draw here. Okay, a little bit wonky, but that's okay. f2 of n is equal to 1 over n. So this is a function that as n grows large, f2 of n grows small. It's also going to stay inside that cone, even though it starts off really big. And so similarly here, we would say that f2 of n is in big O of g of n, or we would simply say that 1 over n is in big O of n as well. Here's another function. So this function is the function f3 of n equals 2n. Now, this function is not inside the cone at all. But remember that we are allowed to scale the cone. We're allowed to multiply g of n by any constant that we want to. And so if I, for example, multiply by 3, then I can make my cone look like this. So this would be the function 3n. So in other words, 3 times g of n. And so my function f3, which is 2 of n, 2 times n, it always stays inside that expanded cone where I've multiplied by a constant, and that satisfies my definition as well. And so I would indeed have that it's the case that this function 2 of n is also big O of n. On the other hand, one more just to get another sense for things. So here's one more function. This is the function, I'm going to go down that way, f4 of n, which is equal to minus n squared. This function is not going to stay inside any such cone. No matter how big a constant I scale by, I'm not going to be able to keep this function inside the straight line cone. And so I'm going to find that f4 of n is not in big O of g of n, or we could also write that as minus n squared, or indeed n squared, either one would be fine, is not in big O of n. So these have been just a few examples of different functions and their relation to the function g of n equals n. So what we're doing is we're kind of seeing, hey, g of n equals n gives us a qualitative way to describe some of these functions. So we, in particular, can say, yeah, these functions grow no more quickly than g of n equals n in some cases. That's true for f1, f2, and f3, but not f4. So the art of asymptotic analysis is the art of trying to find some of these useful, approximate, qualitative descriptions of functions. Soon we'll introduce the formal definition of big O notation, and we'll look at some more of its properties in detail.